Hello and welcome back to a video series on MAC 1105 College Algebra. My name is Sean Perry. These are guided notes number 25 in the series on section 5.3, Properties of Logarithms. The properties of logarithms are tied almost one for one to the related properties of exponents. Let's do a really quick review here of some of the basic ones. They mostly derive from the fact that exponentiation, when we're talking about whole numbers in the exponent place, are going to be related to repeated multiplication. We're multiplying over and over again when we exponentiate something. For example, if I have b to the power of a times b to the power of c, where these a and c are whole numbers, what I'm really saying is multiply b by itself a times, then multiply that by b times itself c times. But this is a lot of multiplication. In fact, we've really just multiplied b by itself a plus c times. And this allows us to go from multiplication between the bases to addition inside the exponent. Similarly, we could do something for log base b of this product. Now, this product, as we just saw, is b to the power of a plus c. And the logarithm of that, the power we would need to raise b to in order to get b to the a plus c, is of course just a plus c. And this is the same thing as logarithm base b of b to the a plus logarithm of base b of b to the c. Well, what have we done? We've gone from having multiplication between these two terms inside the logarithm to addition between two logarithms. This is a little bit different than what happened before, where we had multiplication between the terms and then addition inside the term. Now we have addition between the terms going to multiplication inside the terms, so a little bit of a reversal there. But still something that relates addition and multiplication. Multiplication of these two arguments of the logarithm leading to addition between two logarithms of each argument independently. So let's go through a refresher on the properties of exponents, and I'll show a corresponding property of logarithms to go along with it. We just looked at this one, where if we have multiplication between like bases, it leads to a sum in the exponent. Now, if we have multiplication inside of a logarithm, it could be brought out as addition between two logarithms. Similarly, the quotient of like bases leads to a difference in the exponent, and a quotient within a logarithm can be separated with subtraction. Recall that a power to a power is the product of powers, and so if we have a power inside of the logarithm, we're going to bring that out as multiplication. This might be a little surprising that it's not log of c times log of a. If that seems a little confusing that this isn't log of c times log of a, consider what we would need to get if we took the log of b to the ac. We'd need to get log of b to the a times some c in order to have this, turn out appropriately. So meditate on that a little bit, or just flat out memorize it. If you have a power inside a logarithm, it comes out as a product. This is one of the most important properties of logarithms, is that they can take and step down from multiplication to addition, from division to subtraction, from powers to products. And that's going to be a powerful move. Consider what this would do to roots. If you have a root of index c of b to the a, you wind up putting a quotient in the exponent. This fraction is generally seen, at least for positive b's, as being equivalent to this expression over here. And over here, if we have a radical with index c inside of a logarithm, it's going to come out as division or product by a reciprocal. Same thing, 1 over c times log base b of a. Let's now look at some special cases. If we have b to the power of 0, that's a 1, and likewise log base b of 1 is always 0. Similarly, b to the first power is itself, and log base b of b is in fact 1. B to the minus 1 is equal to 1 over b. And likewise, the log base b of 1 over b is equal to minus 1. See if you can't see why this is exactly just applying this special property and our log of a quotient rule that we saw before. Now, all of these last properties are actually special cases of one cancellation property. And this cancellation property is precisely because logs and exponents are inverses of each other, and inverses cancel to give you the original argument. So if you take log base b of b to the power of something, you just get that something back. And likewise, the composition might work the other way. We're going to see this when we solve logarithmic equations. If I want to get rid of log base b of x, what I need to do is put that whole expression into the power of b, into the superscript or the exponent place of b. I'm taking b to the power of log base b of x. That's also composition the other way. It's going to give us precisely x by the property of inverses. There's one more very important property that we should know about logarithms, and this is how we might go from one base to another. It is in fact arbitrary what base we choose, and this is the reason that some calculators, for example, older TI-84s, TI-83s, etc., they don't have a log base b button. You can't just put in any base you like, and actually, you don't need to. This is a pretty remarkable property because it lets us go back and forth from any base we like, and it might be nice to see where that comes from. So here's a quick proof. If you start with log base b of x, let's call that equal to some quantity y. Rewriting this in exponential form, we have b to the y is equal to x. Now, if I take the log base c of both sides, what I get is the following. And using our power property of logs, we can pull that y out front. Now we just divide log base c of b over to the other side, and look what we have. The original y, which was log base b of x, is now equal to log base c of x over log base c of b. That's all the really common properties of logs, but here's another one that I think is kind of fun. We sort of glimpsed this a little bit in the previous video. Let's see a little bit more of that. Right, to rehash, in our last video, we talked about if I put a 1 over b down here, then that basically pulls a negative sign out. Or you could bring that negative over to the other side and say that the negative log base b of x is equal to log base 1 over b of x. So this is a nice way of going back and forth between, say, like a base 4 and a base 1/4. They really are just vertical reflections of each other. But that sort of brings up this question, and it's a little bit hard to see because we used a -1 for a power down here. What happens if I use some power of a base, right? Is there a nice relationship where I can pull out that power or maybe pull out that reciprocal, move it to the other side? Does this pattern extend to other powers, not just -1, not just the reciprocal of the base? It also gives us a way of reducing radicals in the argument of the log by shifting them to the base instead. This is only for positive values of x, and I'll discuss a little bit of that. But first, let's just look at the basic property. Let's say we had log base b to the power of c of x is equal to y. Rewriting this with our exponential form, combining these with the power rule of exponents, and then taking the log base b of both sides and dividing by c, we're done. So this is, in fact, a trick we could always use. We should always keep the x's positive if we want to say that last property involving radicals. And that's because for certain values of c, we might wind up with sort of an expanded domain. I'll clarify that with a graph, but let's just consider if I was talking about 3/2, right? If c was 3/2, 1 over c was 2/3. Then if I said log base b of x to the 1 over c, right? This is a function which you could define for all non-zero x's. And this is because x to the 2/3 power, or the cube root of x squared, is always positive. And so even negative x's could go into this logarithm happily. On the other hand, if I'm looking at log base b of 3/2, this argument is going to be negative when x is negative. And so we really could only use positive x's here. So this one has a different domain than this one does. So how could they really be equal? Well, let's clarify in the sense that they're equal with a graph. So here I've chosen 2 as my base, just for some arbitrary b to put down there, but I've kept c as being 3/2, as we mentioned. Now, if I bring this to a 1 over c in my argument, we can see that it agrees on the positive x's, right? On the right-hand side here, we have the exact same curve no matter what. On the other hand, there's more to it in the blue curve case. Over here, for negative x's, these are also defined, and we get this lovely little infinite cusp, while before we just had a kind of one-sided asymptote. So we wouldn't call this blue and red curve 100% the same. If anything, we would say that the red curve is kind of a subset of the blue curve. And this is the sense in which they are both alike and different. And what's fun is that we could even see that this is sort of dependent on which value of c we pick. Sometimes they're precisely equal, as it was for -1, and sometimes, we see this kind of flickering thing happen. You might notice this is when my exponent has an odd decimal in it. That's curious. I leave it to the intrepid among you to figure out why that might be the case. Okay, back to the story. One of the things we can do with properties of logarithms is find exact values for logarithmic expressions. And of course, I mean here that we could find that this log base 9 of 3 is equal to 1/2 without a calculator. After all, if we had a sufficiently fancy calculator, we could go to math, log base, and then just type in the expression that we wanted to evaluate. Maybe I want that as a fraction. Or if you have a less fancy calculator, we could still find this out using the change of base formula. For example, I could take ln of 3 and just divide that by the ln of 9, and this would also give me a half. So even if you don't have a log base button, you could still use a calculator to evaluate this. But the question is really, can we use the properties of logarithms to do that? So there's actually a few ways that we could do that. For example, if I rewrite this in exponential form, we have 9 to the a is equal to 3 if log base 9 of 3 is equal to a. Now, 9 is 3 squared, so this is 3 to the 2a is equal to 3 to the 1. And then comparing the two arguments of the exponents, exponentiation is 1 to 1, so we can just set those equal to each other and solve for a. But we also saw a little trick about how to take powers in a base and bring them up as a reciprocal power into the argument. And that we could bring out front because of the power property of logs. Log base 3 of 3 is just 1, and boom, there's another way to get a half. So a few different ways to do this nicely and show your work. It turns out 3125 is 5 to the 5th power. Pull that other 5 up front, the exponent 5 comes out front here, and then log base 5 of 5 is just 1. So we get 5 times 1, which is 5. Here I have the 6th root of 8. I'm taking log base 8 of 8 to a power. That's going to cancel the log base 8 of 8 and just leave the times a power up front. For the next one, we should probably see that 1 over 64 is 1 over 8 squared. This makes short work of it. I'm going to stop with these intermediate steps, pull out that 2 power, cancel the log base something of itself, and that's 2. Same as before. Here's one that's just a little bit spicier, although maybe you know that 243 is a power of 3. Let's see how that might go. So we might write this as equal to b, bring it into exponentiation form, and then know that this is 3 to the minus 1, and a little bit of calculator play might tell you that this is 3 to the 5th. That means negative b is equal to 5, or 5 is equal to negative b. Likewise, we could use our property of powers of a base to bring that as a reciprocal power onto the argument, but the reciprocal of negative 1 is also negative 1. And so we have 3 to the 5th to the negative 1, which is 3 to the minus 5. Log base 3 of 3 to the power of something is that something. That's the cancellation property, and so we just have minus 5. Another classic kind of property is to expand logarithmic expressions. So for example, if I have log base 6 of 5 times 4, or 20 if you like, that's log base 6 of 5 plus log base 6 of 4. This works for numbers. It also works for variables. Log base 2 of 13 times u is log base 2 of 13 plus log base 2 of u. Here we have one where we have ln of e to the minus 6 times z. Let's use the addition property here to separate these logs around the multiplication first. And then we could cancel now. Ln of e to the power of something is just that something. And so this would be our simplified expression. Likewise, if I have log base 4 of 64 times z, I could bring it apart as addition because it's multiplication of an argument of the log. And then 64 is 4 to the 3rd power. So canceling, this becomes 3 itself, and this is log base 4 of z. If we have a quotient within the logarithm, that's subtraction between the two logarithms, which works just as well for numbers as it does for variables. We've used the cancellation property to take 16 and write the log base 4 of that as equal to 2. Notice it keeps that minus sign because it was dividing by 16. Likewise here, we are going to be dividing by v, so we have a minus ln of v in our answer, and we have ln of e to the minus 2, which is going to bring a minus 2 up front here. Here I have log base 2 of x over 13, so all we have to do is separate the numerator, comes up as a positive log base 2, and then everything in the denominator will be in this minus log base 2. So we have log base 2 of 13 being subtracted from log base 2 of x. Here we have a simple application of the power rule, right? If I have a power of this argument, doesn't matter what that argument is, doesn't have to be 3, it could be t. We still bring that power up front as a product, and that's the simplified logarithm. Here's another one where I have kind of playfully done this. Either you could have written this as z to the minus 3, that's 1 over z to the 3, or consider the numerator and denominator separately, right? Then we have log base 5 of 1, which is 0. The log base anything of 1 is equal to 0, minus, because it's in the denominator, log base 5 of z to the third, which, pulling our 3 up front, is going to give us minus 3 log base 5 of z. Exactly what we would have gotten if we had rewritten this with a negative exponent in the first place. Speaking of rewriting things as negative exponents, let's rewrite 1 over the 4th root of v as v to the minus 1/4. Then we can just pull that up front as a product, minus 1/4 times log base 11 of v. All right, next one, we're going to first separate these around the quotient using subtraction between the logarithms, and then we'll pull those powers up front as products, and we're done. That gives us 3 times log base 7 of x minus 17 log base 7 of z. Doesn't matter if we have a fractional base, that's just going to hang out in all of our expressions. What's going to matter is that we pull our powers up front as products, and we separate this product of the arguments as addition. Remembering that the cube root of y squared is just y to the 2/3 power, we're done. We have 16 log base 1/2 of x plus 2/3 log base 1/2 of y. This one's a little bit longer, but it's actually no more complicated. We really just need to apply our rules one at a time, depending on what's going on. I like to take care of my multiplication and division first. That's going to pull out pluses and minuses as such. Then we're going to take these powers, including the 5th root, which is a 1/5 power, and we're going to pull those up front. I want to remark here that the log base 5 of x plus 8 cannot be simplified. Remember, you're going from a more complicated argument within the logarithm to a simpler one out between the logarithms, and x plus 8 is already as simple as we're going to get it. We don't have a simpler operation to step down through from addition, sums or differences within the logarithm, and that includes for all of your polynomials that have been expanded. These have to stay right where they are. You cannot simplify this anymore. This is most certainly not log base 5 of x plus log base 5 of 8, right? Definitely not. Very common mistake, so watch out for that. Once you get down to addition and subtraction in your arguments of the logarithm, that's where it has to stay. So for the next one, I've taken some time just to kind of draw this out and show how the 1/2 of this square root is going to apply to both of these terms. And this would also be something you'd have to consider if you had more than one term in a denominator. That negative sign would apply to all the terms in the denominator. In this case, we have a square root, which applies to both terms in this quotient. Let's see how that looks. So taking the multiplication between the two terms, I separate them with addition. Now this whole thing has a 1/2 power, so let's bring that out as a times a half. And then rewriting this with the quotient rule, we're going to wind up with 1/2 times both of these things. Make sure that this quantity has parentheses around it, because you really do need to apply the 1/2 to both of these things in the same way that both of these things were catching a square root in the original expression. Pulling out my exponents and multiplying that 1/2 through, we get the following. All right, what goes up must come down. If we can expand logarithms, we should be able to condense them too. This is going to be important to know so that you can solve logarithmic equations in this class. So pay careful attention here. Here you can see that we have two logarithms separated by subtraction. If I want to condense them, I need to bring that within as division, right? And then I would wind up with the log of 343 divided by 7, which is 49. That's 7 squared. That should give us a 2. I've written here, though, another way of thinking about it, because we really could have jumped straight into reducing these. There was no reason to condense them first and then simplify. They both simplify independently. For example, log base 343 is 7 to the third, and log base 7 of 7 to the third is 3. Similarly, with 7 to the 1, that's 1, and taking their difference, we get 2. This one, on the other hand, doesn't seem to immediately reduce, because both of these are not powers of 4, they're powers of 2. But we are adding these two logarithms together, which we could condense as 2 times 128. That's 256, which is in fact 4 to the 4. So we could bring the exponent of 4 out front and cancel, or likewise use the cancellation property to get that this evaluates to 4 itself. Here's another kind of grander expression. What I would like to do here is, number 1, bring our powers inside. So I've brought all of the coefficients inside as powers. And I took the liberty of factoring out this minus sign that's applied to both of these, because what I want you to see is that both of these terms being subtracted is going to lead to both of them being in the denominator. So the sum of these two logs would be the product of their arguments, and we're going to subtract that, which puts it into the denominator of a argument. 3 to the third is 27, and w squared, we're going to multiply those guys together to compose our numerator of the argument. And that's the end, right? Now we've written things as a single logarithm. Let's do that again. Bringing our powers inside, we have w to the 16 and z to the third. And then this addition indicates that we should multiply them within the argument. Now we have a single logarithm of this one argument. We've had to step up each time. Remember, products out front go to powers inside, and addition between goes to multiplication within the logarithm. Next, let's bring our 8 inside first. That's d to the 8. And we are subtracting this term, which tells me I'm going to be looking at a quotient. So as a single expression, we have natural log of 9 divided by d to the 8th power. All right, let's hit it again. This time we have some parentheses already in place, so let's do that condensing first, right? Addition between the logarithms is a product within, and now we're going to have to take and raise both of those things to the 5th power when I bring that inside. So I've put some extra parentheses here to make it clear that that's what's happening. Both of those terms have to catch a 5th power. That means 6 to the 5th and b to the 5th. And then we're going to subtract log base 4 of 5, which is going to put a division by 5 into this expression. 6 to the 5th power is 7,776. Sure, calculator told me that. And then we have b to the 5th as the other element of the numerator, and our quotient, because this original term was negative back here, has this 5 in the denominator. Once we've written this as a single log with this one expression as its argument, then we have condensed it fully. All right, let's keep going. Subtraction puts that in the denominator. Addition puts that in the numerator, because we're just multiplying by 27 while we are dividing by 4. Now, we could evaluate these. They're all just numbers, and they do, in fact, simplify to 205 over 2. Next one, bringing our powers inside, we have 4 to the 2 and x to the third. And we are adding them, so I'm just going to multiply these two terms together. I'm starting to skip steps, but I think you can see how you can really just apply these rules one after the other in order to get the following. Now, 4 to the 2 is just 16, and so this simplifies as such. So here we have a 2, nothing to do with that. We have a 3, going to bring that inside as y to the third. We're adding these two terms, so we multiply, and we get log base 5 of 2y to the third. I hope you're starting to see the pattern here, and I think this will very rapidly become some mental math for you, because we are really not changing these numbers so terribly much. We're really just changing our operations while the numbers stay the same. 11 comes inside as a power, 14 comes inside as a power, and subtraction between turns into a quotient within. Here we have some sort of tempting expression that we'd love to simplify, but it does not simplify. It is just a difference within. There is no simplification of that. It's going to stay how it is. So we are just going to simplify the addition between by multiplying those two terms together. If you like, you could distribute that to get x squared minus 9x, and that would be our final expression. Notice the base has never changed while we did any of these problems. However, it will for these problems. We are going to use the change of base formula to convert these to a specified base. Now, really, that is quite as simple as taking the old base, which is a 6, the old argument, which was a 14, and rewriting them as a quotient, where we take the log with the new base of the old argument divided by the log of the new base of the old base. So old base goes on the bottom and the argument goes on the top, and we are now changing our base from 6 to 8 in both of these expressions. So study this pattern about what gets changed, where each one of these numbers go, and what it gets replaced with in each case. Remember, ln is just log base e, so if I want to evaluate log base 7 of 11. Many non-graphing calculators do not have a log base b button. You have to type things in using the change of base formula. So be ready for that. Here they say convert log base 4 of 15 to base 10. That's the common log, so I'm just going to omit the base. That's the usual expression for log base 10. And now we have log base 10 of the original argument divided by log base 10 of the old base. So log base 2.9 of 13, and we want to change that to base 10. Well, I'm taking log base 10 of 13, and then I'm going to divide that by log base 10 of 2.9, the original base. Notice it doesn't really matter how you write your fractions. Do you like them vertical? You like them horizontal? Hamburger style? Hot dog style? It doesn't really matter, right? Convert log base 4/3 of 4 to base e. That's ln. So we have ln of 4, ln of the original argument, divided by ln of 4/3, ln of the original base. If I wanted to change base 9 expressions to base e, I'm just going to be dividing by log base e of 9. So you can also, by the way, I've included this just for completeness. Sometimes that's written as multiplication by 1 over ln of 9. That's just as good as writing divided by ln of 9. However you like to write these things, it's up to you. Our argument, square root of t, that's just going to stay right where it is, right? We're going to take ln, the new log of that, divided by ln of the old base, which was 9. Converting log base 19 of a third root of s to base 10, just as easy. We're going to take log base 10 of the third root of s, the original argument, divided by log base 10 of 19. Here they want log base 11 of negative 3z to go from base 11 to base 2. Okay. Then we're going to take log base 2 of negative 3z, the original argument, and then we're going to divide that by log base 2 of 11, the original base. Alrighty, that's going to do it for this video. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next one.